Welcome back to Physics 142. We've been talking about electric potential, and this video is going to talk about electric potential for many point charges or a continuous point charge. So we've talked about that we can calculate the value of electric potential for a point charge as kq divided by r, divided by the distance you are away from that point charge. So, and that means that if we have like positive point charges, that gives us a very high value of potential. If you have small r, that's going to give you a large value of potential. So if you're very close to the point charge, you have a high potential. If you walk further and further away, the potential goes down. And so we realized that we can think of potential sort of like hills and valleys, where positive charges create hills and negative charges create valleys. We also realized that electric field lines point sort of along the slope of those hills, that electric field lines always point from regions of high potential to regions of low potential. So the next question is, well, what if we have many point charges, right? Many point charges, and what would the potential look like? And the answer is that the potential for many point charges actually can just get all added together. So we can think of it using the idea of superposition, specifically that if we want to know the total potential from a bunch of different point charges, what we have to do is just add up the contribution from all of the different charges. So let's see if we can think about what this looks like a little bit, right? So if we have some positive charge Q, that's going to create some potential. Maybe I have another positive charge Q. Maybe I have some charge negative Q, right? And if I'm interested in what the potential looks like at some spot sort of in between them, what I have to do is I have to think about, well, this charge contributes an amount of potential, kq, over, so maybe this is charge number 1, right? This would be q1, right? Oops, q1, maybe this is q2, this is q3, right? We're going to get a contribution from this charge at this spot P of, this is R1, k q1 over R1, right? The contribution from this charge here is going to be k times q2 divided by r2, the distance that q2 is away, and if it's a negative charge, it'll have a negative sign, right? And then k times q3 over r3, right? Those three things together, that would give me the potential at that spot. Right, so this creates a little hill, this creates a little hill, this creates a little valley. They sort of all get added together. That tells you how high you are at point P. Now, if instead of having many just individual charges, you could imagine I have many charges, right? Maybe they're infinitesimally small charges, or you could even imagine sort of a continuous distribution of charge that I chop up into a bunch of little itty-bitty pieces, right? And so anytime that you add up a bunch of infinitesimally small things from a continuous distribution, we know what that looks like. That's going to be an integral. So the integral of k dq, all my little dq's, divided by r. All right, so for a continuous distribution, we're going to have to actually do an integral rather than just a sum. So let's do a couple examples of this and see if we can understand this even a little more. So the first example that I want to think about or look at is I want to do an example where we think about maybe 6 charges that are equally spaced around some circle with radius r. So you could imagine if I draw some circle, all right, we'll give that circle a radius big R, all right, and I'm going to evenly space some charges around it. 1, 2, I'm going to have 6 of them. So 3, 4, 5, 6. All right. Evenly spaced. Didn't do the best of evenly spacing them, but something like that, right? Sort of evenly spaced. All right, there we go. So I'm evenly spacing 6 charges, and let's make them negative charges. We'll have them be electrons, all right? All have charge minus E. All right, so they'll all have negative charge, because that sounds fun. All right, and the question is, what about this spot right in the center? What is the potential right at the center there? All right, well, to calculate the potential, we just need to add up the potential from each individual charge, right? KQ1 over R1 plus KQ2 over R2 plus dot, 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 right? And so, well, what do we have here? The charge, if we take this to be charge number 1, that has charge minus E, and its distance big R away, right? The second charge here, well, that also is K times minus E over R, right? Also has charge minus E, also has the distance R away. The third one has the same, right? And so if I do that for 6 of them and add them all together, the answer then is just going to be minus 6 times K E over R. This would be the potential right in the middle, right? So this is V in the middle. Great, that's calculating potential. It's super straightforward. It's not a vector, it's just a scalar, so you can just add things all up. But I'd like to actually emphasize something here, that potential is different from electric field, right? Electric field is a vector, and just to emphasize that point, I'd like us to think about what's the electric field at the center, right? So the potential, well, this is sort of a big hole in the ground, right? All of these are sort of valleys, right? And the potential has created sort of a big valley here, right? So it's definitely a very negative number, not a very negative amount of potential here, all right? But what about the electric field at this spot? Well, the electric field, if we think about the electric field from this electron here, right? Electric fields go toward negative charges, right? So an electric field line would look like that. The electric field from this charge, right, would be a bunch of things going toward that one, and toward that one, toward that one, toward that one, toward that one, right? And if you added all these electric fields together, well, this vector will cancel with this one, this vector cancels with this one, this vector cancels with this one. What you'll get is that all of the electric fields cancel, and the amount of electric field in the center here is actually 0. All right? It's a very different answer because here electric field is a vector, and so the directions all matter. Here it's just an amount. We just take the amount of charge minus E, and it comes out to a very different answer. So be careful not to confuse the vector math that we deal with when we deal with electric fields. Just like with forces, that was all vector math. When we're doing energy sorts of things and we're dealing with electric potential, then we're just dealing with scalars. And so you can get very different answers that way. All right, let's do one more example here. An example where we have a continuous distribution, so where we're going to have to actually do an integral. All right, so let's go ahead and shift my whiteboard here. All right. And so the example that I want to do here is I want to think about the electric potential that is at some distance away from the center of a ring. All right, so let's draw a picture of what I'm thinking here. So if I imagine some ring of charge, all right, here's a ring of charge, and here's the center. We're going to come out from the center some distance away to some spot P, and I want to know what's the electric potential at that spot P. Let's define a few things. All right, let's give our ring a radius A, and this is sort of viewed sort of sloping at an angle, right? This is supposed to be a line coming straight out of its center, and let's say that the distance we are away, I'll call that x. All right, so we'll take that to be our x-axis here. Yeah, the question is find v at point P. So how are we going to do that? Well, good question. You remember with electric fields, to find the electric field at point P, we needed to draw in all the vectors and take all the different vector components and then do a big nasty integral, right? Lots of good memories there, I think, for everyone. And we did that by sort of chopping up the ring into a bunch of little pieces, dq, right? So we got to chop up the ring into a bunch of pieces dq. Well, for potential, we again want to chop up the ring into a bunch of pieces dq, right? The formula that we wrote down is that v is going to be the integral of k dq over r. Right? We'll chop up that ring into a bunch of dq's, but because it's not a vector problem, we don't need to draw in a bunch of electric field vectors here. We can just try to think about turning this integral into something that we can do. So to do that, we need to, you can't just integrate q's and r's, right? We need to turn them into variables that are relevant for our problem. And so you might recall that we've done this before, and the way that we did that is we say we want to take dq and we want to relate that to some distance, some path. I guess I forgot to say that our hoop should have a charge density lambda. All right, so we'll give the hoop a charge density lambda. Forgot to mention that. All right. Or, we could say that it has a total amount of charge q. Either way, it gets written, both those ways, right? And so what we say is, well, when we chop this up, we need to relate this dq to the little bit of space that it takes up. And when we talk about little chunks along an arc, the variable we use for taking little chunks all along that arc is we say that's a little bit of space ds, right? And the relationship between dq and ds is this factor of lambda. All right. So we can go ahead and in our integral replace dq. So we'll replace dq. We'll say it's k lambda ds. And then what else do we need to do? Well, we need to replace r, right? We need to turn that into something related to the variables of the problem. And that's something that we're pretty good at by now. We can realize we can draw a right triangle here. And so this must be the square root of a squared plus x squared. And so we'll write for r the square root of a squared plus x squared. Now, with electric fields, we had to take specific components, but here it's just a scalar. No, we don't have to do anything with components. This is just it. So what we can do is we can pull everything outside of the integral that is not an s, all right? And so we'll do that. And so this is just going to be k times lambda, the square root of a squared plus x squared is the integral for ds. And the integral over ds, well, that's the whole path around. That's 2 times pi times a, right? And so we can now write this as k times lambda over the square root of a squared plus x squared times 2 pi a.